Leblanc, Tony Leblanc, from Miami University, United States. Professor José Leblanc talks about synthesis, characterization, and application of carbon dots.
So I would like to thank the organizer of this conference. And I'm very proud because two of the members, I'm thinking about Ahmed Ouriadli, Professor Ahmed Ouriadli, and also Professor Mustafa. And they are really one of my two ex-graduate students. So of course I'm very proud, you know, when you're coming here and I see my students are doing very well. So thanks a lot for this invitation. So my title, Advanced Carbon Dust. Why carbon dust? Because I feel that this type of material might be really useful in the future. And of course, I'm thinking about that electric also materials. So what I'm giving is mainly the work we have performed for the last 2 years, and I did not mention about the work we have performed on quantum dust for about 10 years. So that would be linked mainly on carbon dust and new result also. So the way to dispatch this seminar would be related to carbon dust materials that we know, and that will be followed by 3 preparation of different carbon dots. And you have to keep in mind when you prepare carbon dots, it is very important to think about the application. So the first one would be related from carbon powder. The second one, this is what we call gel-like, and this is quite important because it can be used for thermoelectric properties. And finally, the orange carbon dots, that's another preparation, and this is linked to the 3D printing that we performed recently, about 6 months ago. So first of all, what about the different type of materials in terms of carbon? First of all, the 3D dimension, we know we talked about diamond a few minutes ago. We think about the graphite. In 2D dimension, we know the graphene and also the graphene oxide. In the past, we have done a lot of work on the graphene oxide, in fact. Why? Because you have some moiety on this system molecule, which is only 1 nanometer thick, but this is quite large, micron size. So that's the reason why this is used as a drug delivery system. And we have what I just mentioned about the fullerene, carbon nanotube first, and the fullerene for the 0 dimension, and of course our carbon dots. And I remember when we started this work in 2006, it was related to the fact that this is about compatible materials compared to quantum dots, no leaking of heavy metal and so on. So when I started, as I said, I was able to read all the papers, I would say every week. Now, for 2017, I can tell you, 2018, we have something that at least that will reach about 1,000 papers published. So this is quite important at the moment for the materials. So when we think about carbon dust, as you can see, this is small size particles, and why it is so important because of the level of applications. And in terms of, for those who are interested in nanomedicine, this is really good because this is biocompatible. Those who are working mainly in the field of optics, this is very important because there is an excellent photoluminescence property. And again, the preparation is quite simple. Not when you start, but I would say after 6 months, I think this is quite simple. And finally, on the molecule, the ligands, this is abundant electron donors and acceptors. So that's the main reason why this is so interesting for the system. When it was discovered in 2004, so scientists apply the electric charge between electrodes, and when they use electrophoresis to separate the nanotube, they find out a small spot, and this small spot was due to the carbon dots, and it was shown that it was really highly luminescent. And if we irradiate these carbon dots with visible light, and we use some filter. I have a problem with my system now. So when we use a filter, we can see different color. We can detect, in fact, different colors from the blue up to the red region. Or you can excite the carbon dots specifically at different wavelength, and you have the same wavelength that you can observe. So as I said, this is really important because of this high intensity, much higher than fluorescence chromophore. because the quantum yield might be up to 80%. So that's very important, and this is very stable also. So saying that for the carbon dots, if we think about the approach, as you can see, we have the top-down and also the bottom-up approach. And for the bottom-up approach, as you can see, we have this microwave, the ultrasonic, thermal, and for the top-down laser ablation, arc discharge, but also what I call the hydrothermal effect for these different ways to make the carbon dots. So this non-toxic carbon dots, first of all, we started with the top-down approach, that means carbon powder. And with this approach, we can see that the way to characterize the carbon dots are mainly absorption, UV visible absorption, and fluorescence spectroscopy. And just to mention, there are 3 types of carbon dots, and these 3 types in fact correspond to what I mentioned about the outline, saying that the top-down approach with the carbon powder, and the second one is gel-like carbon dots, which is bottom-up, and this is also bottom-up approach. So for the first preparation, as I said, there are 2 bands mainly. For whatever the preparation you are making, there is one n-pi transition at around 325 nanometer, and we have another one which is a pi-pi transition, which is due to sp2 orbitals for the carbon dots. For the luminescence property, that's the fluorescence property. As you can see, for the first preparation with our carbon dots, there is a wavelength dependence. So that's the normalization of the wavelength. So when you excite, you see I don't have mine, that's a problem. So when we excite at different wavelengths, starting, for example, at 300 nanometer, and we increase the excitation wavelength, there is a shift from the blue to the green region. And this is true for the second preparation also, which is the gel-like. And finally, the third one, which is the orange carbon dots. And we mentioned what is this preparation. So there is independent, the wavelength of excitation is independent for the emission. So that's important because when we started this work a few years ago, when we're able to make our carbon dots and we're able to see the wavelength excitation dependent, we're very happy. Because we said, well, we have truly the carbon dots. But in fact, this is not real. What I mean is there is a possibility to have a specific system to make a carbon dot which is wavelength independence. So saying that, let's go back to the first preparation. But before that, if you ask me what is the mechanism to explain there is a wavelength dependent in terms of excitation. As you know, for those who are doing fluorescence spectroscopy with fluorophore, organic fluorophore, you excite a different wavelength and the emission will be always at the same position. And that means you have this transition here, excitation of the electronic state to the first electronic state, fundamental state. But for the carbon dots, you have what we call surface state. That means you have different, I would say, atoms at the boundary between surface of the carbon dots and vacuum, that there is some state there that you can emit. And that's the reason when you excite a different wavelength, you may have different emissions, as we mentioned here. So that's for the what we call the quantum confinement for the carbon dots. So saying that about the preparation, now we're talking again about the carbon powder and the bow applications. So first, as you can see, this is very simple for this preparation. We use carbon powder. As I said, this is what we call the top-down approach. And we use oxidation of our carbon powder. And oxidation means using nitric oxide and also the sulfuric acid, and heating at 100 degrees centigrade, neutralized by sodium hydroxide. And finally, what we have after dialysis to purify our compound, we get our carbon dots. And what is important, any carbon dot, this is the ligation, what is on the surface of the carbon dot. That's very important. So, as you can see, for this particular way to prepare the carbon dots, we have 5.8 millimole of carboxylic acid per gram of carbon dots. So that's very, very important for conjugation eventually. So what is important when we prepare any carbon dots is the characterization. And we took at least 1 or 2 years just to make sure that we have the right property, we are able to reproduce carbon dots with the specific, I would say, photophysical properties. So to do that, what we have done is to use the Fourier transform infrared spectroscopy, ATR, attenuated total reflection. And what is important is to compare the ATR spectrum with the X-ray photoelectron spectroscopy. What I'm saying is for any band like OH band, and also NH band in this position here, and we have the position of C double bond O, C, O, and so on, there should be a correlation with XPS. Why? Because XPS look only the surface, not more than 100 angstrom on the surface. And the Fourier transform can go down to micron size in terms of dimension. So that's important to see this correlation. Second, what is the thickness? We use two methodology, transmission electron microscopy and atomic force microscopy. So for this particle, we're using the carbon black. So we have seen that the size of the particle is 4 nanometer, and they are spherical particles. So in terms of application, for the non-toxic, we call it non-toxic because there is no leaking of the carbon dots. So we have applied to different systems, and I will not mention all the systems here, but we use it for the protein fibrillation inhibition. The first one here, mainly with for the Alzheimer's disease. That means A-beta 140, 142, so we can inhibit it. Now, we have to cross the blood-brain barrier if we want to use this inhibition effect. So I've done some work also with carbon dots and transferrin, and we know using a model system, this is the zebrafish, we're able to see that it crosses the blood-brain barrier, so to go to the brain. And third, we will talk a little bit more about the bioimaging for the bones corresponding to a model system. This is zebrafish we use. And for drug delivery, we have done also work with the Department of Neurosurgery about the brain cancer tissue cells. So this application has been already performed, but I will, as I said, I will concentrate on the bioimaging. Why? Because when we inject in an animal system, and we use zebrafish, why? Because it's much less costly than mouse, that's the first reason. And second, all the elements, like I'm thinking about heart, lung, kidney, has exactly the same system than ours. So that's the reason why we use it. What we find out is when we inject to the heart of the zebrafish, we can see all the blood circulation because it's living. And we're surprised to see that there was a bones imaging here. And our carbon dots that is prepared, the non-toxic carbon dots, has not a high luminescence, maybe 2%. And we're surprised to see that there is really imaging of the bones for the system. So saying that, what we have done is to, first of all, we use a protocol I just mentioned for the preparation of the carbon dots using carbon powder, as I mentioned here. We inject it to the stomach or the heart, it's the same thing. And we look by microscopy. We look the zebrafish using the microscope, fluorescence microscope on this point. So saying that, what we find out is when we inject it into the system, and we use the blue excitation, because as I just mentioned, we have a blue excitation, we may have orange excitation, because it's excitation wavelength dependent. So we have different emission. So if we use an excitation in the blue, so we can see the bone formation for each of this system, and this is when it's blue, we see the green emission. If we use the green excitation, so we see the red emission. So we have really the quantum dots, the carbon dots really in our system. So the control experiments, we don't see anything. Sorry. we don't see here the bone formation. And when we use after 6 days the CDOTs, we have the formation of the bones here. Same thing here, more evident here. So this is the bioimaging. And the question was to know, is it really specific for this type of carbon dust preparation? The answer is yes. Because if we use another preparation, we don't have the same I would say, view in terms of bioimaging. So for the wild type imaging, and as I said, if we look with the carbon dust we injected, so we can see, sorry, I will just take this here, we can see the bone here imaging. And if we use the retinoic acid, we know that the system that grows the bone, again, we can see much clearer the bone's formation. But if you use a derivative, the benzaldehyde derivative, which is eliminate the growing of the bone, we don't see it here. So that means that when we convert or conjugate different ligands onto the bones, not the bones, sorry, onto the carbon dust, it will recognize or not the bones, depending on the conjugation you are making. Another way to look at it in the synthesis of different carbon dusts, and the first one I just mentioned is the one on the carbon powder. The second one, this is what we call the bottom-up, using citric acid and ethylendiamine. This is a citric acid here, ethylendiamine. And finally, the third one is related to mainly citric, sorry, is related to the citric acid, again, with polyethylene glycol, diamine, that's the second one here. And we have diphenyl benzene here. So we have 3 preparations and we inject it into the zebrafish again. And what we find out is, for the first one, we can see the bone formation here. And if you look the second preparation, we don't see any imaging of the bone. And the third preparation, we don't see any bioimaging of the bone too. So that means for the first preparation, that's the only one using the top-down approach that we can detect the bioimaging. So this is really related to what I call the preparation of the carbon dust. Second point I want to mention is the chemical modification of the first one. So if you modify with the carbon black, when we start the carbon black to make the carbon dust, and we conjugate, in the second case, the diethylenamine. So the first one, this is the same. This one's the same as what I have shown here. But the second one is related to the ethylendiamine that we put onto the carbon dust. And again, we see the bone formation also in this case. So that's here. And the third one is using glutamic acid. We know glutamic acid like the bones. So again, we can see the formation of the bones using the glutamic acid. Bottom line, the conclusion of this work is to say we were able to see the bones formation when we inject into the heart of the zebrafish our carbon dust, but only if we are working the top-down approach using the carbon black to make the carbon dust. So saying that, if we look about the mechanism, we are not able, in fact, to really to prove what is the specific mechanism to see this bioimaging. As an example, we have used the calcium, because we know calcium for bones is very, very important. But when we add to this calcium concentration, we have a concentration of carbon dust of 0.01 milligram per milliliter. We don't see much effect. And if we use another system, and this is the hydroxyapatite, one constitution of the bone is hydroxyapatite. So again, this particular molecule absorbed in the same region as the carbon dust. So that's the reason why it was impossible to say that what we are observing is due to hydroxyapatite, as an example. And the third example is we use one of the constituents of the bone. This is the cartilage or the bones, is the chondrotein. And even in this particular case, again, we have a fluorescence of this molecule, which is in the same region as the carbon dust. So it is difficult to really to pinpoint what is the mechanism. Question is open. If you have any idea about the mechanism, I would be most pleased to hear about it. We'll do the experiments right away. So the second aspect of my talk is related to the gel-like carbon dust. And we have proved about a few months ago only that there has a huge thermoelectric properties for this gel carbon dust. What is the way to prepare this this carbon dust? Is again simple molecule, which is the source of the carbon atoms. And this is the citric acid, which is very important. It is used extensively to produce the carbon dust. And if we add the ratio 1 citric acid and 14 ethylene diamine, so we heat it and we can dialysis and we form a gel, in fact, for this system. And if you put upside down your vial, so this is truly a gel formation. And we have done all the rheology property from the lab in India, so that has been published last year for this system. And Tyndall effect, of course, if you use a pointer and you are able to see that there is a scattering of the light because this is very dense liquid, supercritical liquid. So we have, as usual, we have measured the fluorescence property, absorption, fluorescence, atomic force microscopy for the thickness, and also the TEM, transmission electron microscopy, and FTR for each of these preparations. This one too. Now, for the idea was to say, if I had to form a gel, we wonder if the electrostatic interaction is important. In fact, it's yes, because if you use a salt like calcium chloride, or you use the sodium chloride, there is a precipitate for both these two salts. So that means the hydrogen effect, hydrogen bonding is very important in this formation of the gel. So the point I want to mention is, we said, well, if I have this bulk in terms of gel, carbon dust, is it possible to separate them, separate the particle, although the thickness is the same? Thickness means AFM for the Z resolution, TEM for XY resolution. And in fact, this is the same. So what we have done is to use a simple technique, thin layer chromatography, and we're able, in fact, to separate 4 different, I would say, bands. And if you look at the different bands here, at least 2 bands has the same absorption, same fluorescence. That means whatever the excitation wavelength, you will get the same emission for number 2 and number 3. So that means in the set of carbon dust, although the size is the same, it is possible that we have different conjugation onto the carbon dust. And this is what we have done to show that there is a different conjugation. And that means different property in terms of UV and also in terms of fluorescence spectroscopy. So that's important in terms of application. So saying that, what about the thermoelectric effect? As you know, if you have a system that you have a cold and a hot, I would say, difference, so the difference of temperature, you can induce a current, you can induce a voltage. And we apply it for our system, and we use telluride, bismuth telluride, 2% of the carbon dust, the gel carbon dust. And what we find out is when we look, first of all, for the characterization of equipment, it's not so important, for the measurements of the conductivity, and also for the Seebeck, which is very important coefficient characterization. We use also the thermal conductivity measurement to assure that really there is heat release before to induce the current. And what we find out, as you can see on this slide, is that when we add 2% of our carbon dust and we look about the electrical conductivity, we have a huge increase. And if you look at the power efficiency, converting the heat to the electric current using 2% carbon dust, we have 70% increase. And when we received this type, when we got this type of result, we were very surprised. And of course, my colleague from College of Engineering did not believe it. He sent it to another lab in Florida International University. He sent it to Istanbul for his friend, and he got the same result. So that means we got this result about 5 months ago, 6 months ago. Now, of course, NASA is very interested for this type of work. So we project to send a proposal to the NASA. So that's an application. And I know my colleague in Maroc, they have used also carbon dust for dielectric measurements. Also my colleague, Professor Luis Costa. So I'm sure that there will be huge application in the near future. So this is one type of application. And of course, as you know, this question of Peltier effect, and we know that at the moment, many companies are interested to use the heat coming from the head and using this shielding, shielding just here on the head here to convert the heat from the head to the electric current. So if you have this efficiency of 70% increase, that would be a possibility to use it eventually. Same thing for the seat, as you know, in a car. At least I'm coming from Quebec, as it is very cold in winter, believe me, minus 40 degrees centigrade. So if you're able to convert the heat to electrical power, that would be great. So it's just to show you two applications of this system. This is for the gel. And other experiments we have done in terms of application is to use a printer and to replace the ink by the gel carbon dust because it's highly luminescent. So what we find out is there is an application because we have invisible ink, in fact, using gel carbon dust. And that means that when we when we write a text, as you can see, the definition of this text is really, really good because when we look the text itself, so you can read it very easily. Now, if you have the white light, if you use white light, you don't see anything, nothing at all. Sorry. So with the white light, so this is a blank page. But if you use the pointer, blue pointer, you will see your text. So that's a way to write to somebody that you don't want to see other people to read it. That's a possibility using this gel ink. Another, again, this is the fact that we can erase it too. We can erase it, we can print out, we can reuse the same page, in fact. So only with a drop of water you can erase it, and after that you can rewrite it again. So, and again, the main point is the fact that it is not visible to the visible light. So we can also, for the fingerprint, we can do the same thing too. We can have a better resolution. This one, we have done it very quickly. So for 2 students who print their thumb. So this is a printing again. So counterfeit, we can work on it, knowing that this gel carbon dust, we can have a few applications, as you can see. So the other one I want to mention briefly is the one related to the orange carbon dust. There is a solvent effect, and we're able to do the 3D printing for this type of carbon dust. Again, quite easily to prepare. This is the acetic acid, which is the source of the carbon to produce the carbon dust, and 1,2-phenyldiamine. So when we do that, we are able to produce a system, luminescence in the orange. And as you know, this is important to have a system in the red region, because if you want to apply it in bio system in nanomedicine, you need it in the red to make sure that tissue will not absorb light. That's the main reason for that. So saying that, for this preparation, so when we look the carbon dust in different solvent, as you can see, depending on the solvent that we used, so we have different color, and that means we have what we call solvatochromic effect. So using water on the left side, methanol, acetone, and on the right side, the tetrahydrofuran. So that's very, very important for the application. Another system type of application is 3D printing. So what we're able to perform is to add the carbon dust to the polymers, and we need a very low concentration of carbon dust. This is 1 carbon dust for 5, I would say, molecule of the polymer. So that means a ratio of 500:1. And in this particular case, if you use any system that has absorb the carbon dust. So we have seen here, we can see 2 different type of, I would say, bubble that can absorb the carbon dust. And when we shine light, of course, we see different color. With visible light, this is transparent, so there is no problem. And finally, we're able to make a Liberty statue using the carbon dust. And that's the experimental. When we shine light, with the blue light, we can see the orange presentation. If you use the control experiments with the visible light, we don't see any luminescence coming from the statue. So that's very important, because for the 3D printing, the color is important too, and we don't know at the moment how to make it with the right color. But we think that with the carbon dust, yes, we'll do it. Now, the application of cosmetic is mainly for the student who came from France, came to my lab, and as you know, at least in France, I know a few of my colleagues, they like cosmetic. So we asked them, can we have a look on the cosmetic using this particular orange carbon dust? And they asked me the question, why you want to use it? Well, when you go to the nightclub, that would be quite nice, to have some color on your system. Said, why you're saying that? Because I went to also nightclub myself when I was young. I'm too old now. But I was young, yeah. When I gave my seminar in the evening, believe me, I went to the nightclub. So saying that, we started with the nail. So we put the carbon dust into the nail solution. And when we put the solution onto the nail of a woman, so with the white light, we don't see anything. But using the blue light, like a pointer, for example, we see the yellow color. So that was the first application. Another one was to use the hair. Why? To put in an emulsion. I'm taking about shampoo. You put the carbon dust in the shampoo, and you have different colors. Blue can have orange. And if you have white light, we don't see anything. So when the water is released, when the water is evaporated, you are sticking the carbon dust onto the hair. And that means that we're able to see, in this particular case, when it's visible light, we don't see anything. When we use a blue light, we can see the difference of color for the system. So in summary, what I have shown was, the first one was related to the top-down approach, the carbon dots, using the carbon powder to produce it. And of course, there is a huge application with the zebrafish. The second one was related to the gel. The gel is quite important because this is very stable and you can apply it on different systems. And for the orange carbon dust, the main reason was to go into the red region so that we can apply it in nanomedicine. And I would like to mention that without my students, will not be able to make it. So before to show these students, what we are doing right now is to use our carbon dots that might be transported to the blood-brain barrier of the zebrafish, and we've just started the animal study with the mouse. Another part of our system is to use the specific drug delivery to bones, I just mentioned here. And another system is related to, mainly related to the emission of the carbon dust in the red region so that we can apply it for the brain, I would say tumor, cancer cells. So saying that, that's the group that I had. And I would like to say that all these people, mainly the postdoc, they helped me a lot for this type of research. And my collaboration is mainly from University of Miami with Dr. Skromny, related to the zebrafish. We have Dr. Selick from engineering about 3D printing, Dr. Graham on the neurosurgery department, and finally for the XPS measurements with Professor Chusui from Middle Tennessee State University. So I would like to thank you for your attention.
Thank you, Professor, for this presentation. Some question?
Firstly, I would like to thank you for your talk. It was very interesting for me because my thesis work about nanocomposite based on carbon dot. Yeah. So my short question about what's the difference between the carbon dot and the carbon quantum dot? Are the same or not? Are the same?
Yeah, for the abbreviation about thinking about carbon dot, there are 4 or 5 different applications in terms of name. So we say carbon dots, carbon quantum dots. There is another one related to carbon nanostructure. This is related to carbon dots. So they're all the same. Yeah.
Okay, thank you.
Thank you for the talk. I'm a little bit surprised about this zebrafish still in life over more than 6 days when you include the quantum dots or these quantum carbon dots. And because it's very known that the interaction between carbon, for example, nanotubes or nanoparticles, they have stopping. This nanoparticle stopping axonal growth during the development of the brain. And here zebrafish is still in life over 6 days. So, and but the second question is how you can motivate or using the grafting of IDEA, ethyl-diamine and nanoparticles. You modify chemically the nanoparticles with amines, amine terminated.
You're right, yeah.
So this is these molecules are more complicated to stabilize and to have only amines on the surface. So maybe if quantum dots or carbon quantum dots are efficient with this between brackets naked surface, why using IDEA? And I have, if I have time, I have some comments on the calcium movement and calcium application in this in your experiment. So thank you for answering these two comments and questions.
Yeah, you had three questions. First of all, for the carbon dot and zebrafish, why we use using zebrafish for 6 days. So the main reason is because we can see it using fluorescence microscopy. We can see the carbon dots in different part of the zebrafish, lung, for example, kidney, stomach, and so on. What we find out is after 1 day, all the, I would say, carbon dots are eliminated. And was surprised because if you think about quantum dots with cadmium, selenium, for example, cadmium will be stuck into the kidney, or mainly the kidney and also the liver, but not with the carbon dots. Carbon dots is carbon. Our system is made of carbon. And I think that's the reason why we have a huge biocompatibility. And after 2 weeks, the zebrafish is still living. We don't see any difficulty, any problem with it. The second question was, I would say, related to mainly the I would say, functionalization of the carbon dots. The fact that we have carboxylic group, if you have any NH2 group like ethyl-diamine, you will have a conjugation, a huge conjugation, using for the chemical, I would say, functionalization, CDC and NHS. So you have a covalent bonding between carbon dots and the ethyl-diamine. So it's true for protein also. We do the same thing with protein. And finally, we just started to have a look with older zebrafish, not 6 days, but to go, for example, for 2 weeks. But it was related mainly to the bone. Now we are doing this type of work at the moment with the bones. Now, just to pursue what I'm talking about, only 2 studies has been published about, again, carbon dots injected into the mouse. What they find out is when you inject it into the heart or you inject it to the tail of the mouse, I mean, everything is ejected after 6 hours. And we're expecting that probably there will be accumulation in the kidney because, or the liver, because the urine is could go out from the kidney. But no, there was no accumulation. And that's the reason we want to do the same type of work in mouse also, just to make sure no accumulation.
So I have a small question because I was curious about the graphic of thermoelectric effect that you present, that the conductivity versus voltage,
right,
that is not linear, and they showed 3 curves with different colors. Remember in the slide?
Yeah.
What is the difference between these 3 curves?
No, there is one curve which has nothing in. There is no carbon dots. This is thallium. This is the bismuth telluride only, the materials. The second one is we put 1% of the carbon dots. And the third one was 2% of carbon dots. So increasing the percentage of carbon dust will increase the efficiency of the conversion between the difference of temperature and the electrical part of it, or voltage formation. And the main reason for that, I think, is due to quantum confinement. That's the main reason. Because if we use a different type of carbon dust, it does not work. So it works for a specific type, I believe, of carbon dust.
Okay, finally, a comment. It will be nice if I can have this carbon dot shampoo.
Yeah.
And I can put my white hair to black hair when I go to the nightclub, and then everybody thinks I'm really young.
That's right. That's right.
It's a good application.
Yeah, I agree with you, and you can start a company, you will be rich. I think so.
Yeah, okay. Thank you very much indeed.
I have my last question about your technical aspect of your talk. Concerning the bio-application of non-toxic carbon dot, first of all, why did you call it non-toxic? Did you try it for the human body or not?
You know, if I was trying with the human body, I think that FDA will send the FBI to my home.
Second question. So you give a good illustration of discotheque, and you say in your talk you said something about cancer therapy, drug delivery. So I would like to see do you have any progress in this area?
Yeah, I did not present any result, but we have very, very nice result. Why? Because we use doxorubicin. Doxorubicin now is used, I would say, extensively, whatever the type of cancer you have. And what we have done is to use the tumor cancer cells and from the brain patient. And what we found out is when we conjugate the doxorubicin, we reduce about 50% the cancer cells. If we use two drugs for the conjugation, doxorubicin and epirubicin, we find out that 95% of the drugs are efficient. That means 95% of the cancer cells are killed. Very surprised, and we're writing the paper on it. But before to send it, we want to maybe to have a patent for the system. Well, it works very well with a double conjugation. And again, I mean, carbon dust is used as a nanocarrier. It's only 4 nanometer. We can produce carbon dust at 2 nanometer. And that's the reason we can cross the blood-brain barrier. So for cancer cells, again, it crosses the cell membrane, no problem, because of the small. And we can use the receptor, transferrin, for example, receptor, that the membrane recognizes the transferrin and let the carbon dust inside with the drug. So that reduces, I would say, greatly the cancer cells. The cancer cells die, no doubt about it.
Dear Professor, thank you for your exposition. It is very interesting for me because my thesis is working about hydroxyapatite and doping, co-doping with the carbon nanotype, graphene, and carbon dot, and its family. So my question is about hydroxyapatite and carbon dot. If you interested to doping or surface deposition of carbon dot in surface of hydroxyapatite. This is my first question. Second question is about bismuth electrical conductivity and after doping with the carbon dot. And thank you very much.
So for hydroxyapatite, we were not able to show that hydroxyapatite has a huge effect on the carbon dust. We just look about, even with bones coming from whales, I mean, we crush it, and see if there is a possibility to see bioimaging using carbon dust, and we're not able to see anything. What we're able to see is if you have a crack in the bone, so that means there is release of calcium. So we expected that maybe with our carbon dots we will be higher intensity of luminescence. And the point is, yes, there is a higher intensity. That's the reason why after that we have done the work with calcium, but we're not able to show a direct effect of carbon dots on the calcium up to now. Now, as I said, I mentioned the word bone. Yeah, but fish is not bone, it's cartilage. And I wonder if when we inject it into the heart of the zebrafish, if there is a possibility for carbon dust to have a corona proteins. And if I have a corona protein, specific protein, that might be the one that interact with the bones. So you see, the mechanism is quite complicated at the moment to know about it. But NIH was interested because we got a grant from NIH to work on the osteosporosis using carbon dots. So regarding carbon dots for the human being, well, we just thought we need to go to the FDA approved. And as you know, it takes 3 years or 4 years before to get it, plus maybe $100,000 to go to FDA approved. And that's a lot of money.